Okay, let me start by thanking the organizers for being here. Well, for me being here. It's my first time to Bangalore, and I'm really happy to see this nice place. I have heard a lot about it, of course, but it's the first time I really see it. So I want to talk indeed about mainly empty states, and also a little bit about you. And you could rephrase the title of my talk as, let's walk towards self-consistency in these GW+DMFT kind of calculations. And let me start my talk by two provocative statements. The first is that I believe that if we had had as much inverse photoemission data as we had photoemission data, LDA+DMFT techniques would never have, at this stage, the reputation of being such a successful method. So I think much of the success of LDA++ techniques owes to the fact that we have more focused on photoemission than on inverse photoemission. I will explain you why. And this is not a problem of DMFT, but a problem of what is in front, namely of LDA+. So I will ask the question about the LDA starting point again. And my second provocative question is, does the Hubbard model actually exist for the purpose of describing metal insulator transitions? And, well, my tentative provocative answer is yes, but maybe twice. Once for the metal and once for the insulator. I will also show you why. So I'm in the very lucky position that Atsushi Fujimori gave me an introduction to the material, a Ferdi to the methodology, so I will just go very quickly through that. Well, the first motivation to combine GW and DMFT, on a very basic level you could say, is you want to combine the best of two worlds. GW has a nice description of screening, but as a perturbative method cannot go all the way to the strong coupling limit. Dynamical mean field theory has this ability to describe any correlation regime, but doesn't say you anything about screening. So that means Hubbard U has to come from somewhere else as an additional input, even if you calculate it from somewhere. So if now you combine these two things, the hope is that you can do screening from first principles and still do it with a framework that allows you to go up to the strong coupling limit. So Ferdi has shown you that this comes at a price. At the price of quite complicated equations. So you have seen that essentially you have a self-consistency loop for both one-particle quantities and two-particle quantities, Green's functions and Green-Coulomb interactions related to the polarization and so on. And just to show you the comparison to DMFT, that would look like that. So here you have the solution of an impurity model and a self-consistency, and you iterate this loop. And what GW+DMFT is doing now is to essentially add you an analogous loop for the two-particle quantities. This is only what I will call the inner loop, the loop to converge the quantities for a fixed GW calculation. That means for a fixed non-local self-energy and fixed non-local polarization, just to converge the local quantities. And then you can even have an additional outer loop that would kind of relate this here to also converge over the non-local quantities. So this is what I will refer to as the GW self-consistency. So now Ferdi has told you that, that for this reason, so the equations being so complicated, current implementations have always made some simplifications. So when we started this business in 2003 with Antoine and Ferdi, we did a very simple, well, not actually even GW+DMFT calculation, but a calculation where we combined the self-energy of an LDA+DMFT calculation with a non-local part from GW. That was for a purely static Hubbard U, just fixed at the outset. So since then, things have evolved a little bit. So for example, in this work of Strontium vanadate that Ferdi cited, people have tried to get rid of the LDA, replacing it by a quasi-particle GW calculation. However, then you have the problem that you cannot simply do the subtraction of the local part of the self-energy, as Ferdi explained to you. So you will have actually a double counting, and that means if then you put frequency-dependent U, you would vastly overestimate all renormalizations. So Ferdi showed you a way to properly do this double counting correction. So essentially using the self-energy of the LDA plus DMFT, but with frequency-dependent U, and subtract from the GW calculation the local part. So this was very successful, as he showed you. I will focus on the last two works here, where we add the self-consistency, let's say, in the inner loop. That means for the DMFT part, for a fixed GW, we fix U from constraint RPA, we fix non-local sigma and P, and then we iterate over the local quantities. And I will show you this for Strontium monadate to substantiate my claim on the empty states. And in the very final part, I will show you quickly a fully self-consistent calculation on both loops this time, but in a very simple setup, namely for a material where, luckily, you can cook down everything to one orbital model. Okay, so this is why I called my talk also towards self-consistency in GW plus DMFT. So now I don't need to say much about the material, the first material anymore, strontium monadate. You have seen the nice photo emission data from Fujimori with the quasi-particle peak here coexisting with the Hubbard band. And you have also seen the photo emission plus inverse photo emission data. Ah, great, thanks a lot. Oops. Okay, good, thanks. With, in particular, this feature at 2.7 eV, that was early on interpreted as an upper Hubbard band. I will not repeat the nice discussion of photo emission, inverse photo emission. Here you have seen the mass enhancement estimate of the order of 2. And you have seen the, let's say, standard LDA plus DMFT picture. LDA plus DMFT calculations performed traditionally just in a T2G manifold with a static U give you a kind of three-peak structure here with quasi-particle renormalized and lower and upper Hubbard bands. And then the conventional interpretation was that you should interpret the photo emission, inverse photo emission picture here with lower Hubbard band, quasi-particle peak, upper Hubbard band as a realization of this three-peak structure. And this is the point where I'm going to take issue with. But let me step back first and look at everything on a larger scale. So I will not focus only on the T2G states, but I will check here oxidant states. This is T2G, EG part, and also the strontium. Oops, damn it. Sorry. And also the strontium D states here. And if you look at the picture at this scale, it's obvious that, of course, there is a problem in the T2G manifold here. The LDA gives you a nice peak. The photo emission has this renormalized quasi-particle Hubbard band here. And then here, as Atsushi Fujimori mentioned, in this data, maybe there's some surface effect that the peak should actually be somewhat bigger. So we have all the questions about the T2G manifold, but we have additional ones. We have oxygen P states, which are way too high. We have strontium states, which are way too low in LDA. So this should not come as a surprise, because we are also in other materials not expecting LDA positions to be at the correct place. If you were looking at strontium titanate, a band insulator, you would say, okay, the position of these states is not correct, I should do GW calculations. Okay, let's try that. Let's do GW. Okay, this I don't have to comment anymore. Ferdi showed you the band structure, T2G within GW. Let me focus on the large scale picture. And then you see that, well, the oxygens, they move slightly in the right direction, but you're not completely there. However, you get a very, very nice description in the unoccupied part. In particular, you have the strontium D states here, practically at the good position. This is not a surprise. This is just nice. And then there is a surprise, because here, 2.7 eV, that was the inverse photo emission peak that was interpreted as the upper Hubbard band. But now we have actually here the EG states, which have been moved up. So this picture suggests strongly that this peak is probably dominated actually by EG states and not an upper Hubbard band of T2G character. Okay, let's move on. Let's analyze the self-energy a little bit. Well, this is the real and imaginary part just of the GW self-energy. And what you see is that, well, in some regime around the Fermi level here, you have a linear regime. However, you have an offset of occupied and empty states, and that corresponds to shifting up of T2G states. You can analyze the non-locality of the GW self-energy here by defining something like a generalization of a quasi-particle residue, so just something which would be quasi-particle residue if you were on the Fermi level here. So the derivative of the self-energy at a given k point. And then you can look at more or less the variance of this quantity, and this is what is plotted here. And what you see from there is that compared to the local renormalization, indeed, this variance is small in some window around the Fermi level, but it is relatively asymmetric between occupied and unoccupied states. Okay, so now let's combine things. Let's do GW plus DMFT with self-consistency within the inner DMFT loop. And let's plot things on a whole scale. I should add one technical caveat, namely, we did this in what we called an orbital separated scheme. That means we did the DMFT for the T2G and took local parts even local parts for the other orbitals from the GW. Then what we get is that somehow by construction we conserve the description of the oxygen p states and the strontium d states. So here things stay nice. And we correct essentially the T2G manifold. So we have now this renormalized quasi-particle peak here. We have the lower Hubbard band in agreement with the photo emission here. The photo emission experiments are in black. But we keep the description of a peak here which is not of T2G character. In fact, we do not identify here a clear upper Hubbard band of T2G character. So maybe I should walk you through these curves more slowly. So the solid curve is the total GW plus DMFT, and what is the dashed one here is the T2G contribution. And this shows you that, in fact, you have here in this region some broad feature which extends to more or less 2 eV, but which is not responsible for this presumed upper Hubbard band. Let's zoom on the occupied states to make sure that things are still fine. Quasi-particle peak, lower Hubbard band at the right position here, 1.6 eV more or less compared to experiment. And now let's analyze things a little bit further on the other side. So this is a comparison of the experimental photo emission data with the GW plus DMFT spectral function at chosen k points. So we looked at the gamma point here and the x point. And, well, that looks nice. You have here this comparison for the gamma point, for the x point, for the occupied states. Now, if we look on the unoccupied part, let me focus on this figure, then you have a little surprise. Namely, if I look at the x point, so these are these blue curves here, the x point is where the initial LDA band had a value of more or less 1 eV. You see that, well, the GW plus DMFT peak is again at about nearly 1 eV. So it looks as if this is nearly unrenormalized for the unoccupied states. There's a strong renormalization, as discussed before, for the occupied part with a factor of 1/2 and so on. But on the other side, things look pretty much different. How can that be? Well, let's step back. Let's see what we really did. So let's go back to something that I would call the pseudo-bare band structure on which we want to do DMFT. And I defined that band structure not actually directly as a band structure, but as the self-energy that I would obtain just from non-local GW. So I calculate the GW self-energy, I subtract the local part, and then I look at the spectral function corresponding to that artificial self-energy, which doesn't have local renormalizations, but everything else. So this is obviously, by construction, the closest possible to something like a bare band structure on which you would like to do just a DMFT with a local self-energy. And let's look what this looks like. Well, that's the answer. So compared to the LDA here in red line, you have this is this non-local pseudo-bare band structure. You have nearly the same for the occupied states, but you have a substantial band widening, well, more or less 1 eV here, on the unoccupied part. So this band widening is the exchange effect discussed by Ferdi. It is a screened exchange effect. This is why the band is not as wide as in Hartree-Fock, but it acts rather selectively here on the unoccupied states. The EGs are not plotted in the GW. No, that's just like this. Okay, just for comparison, that was the GW self-energy. So that has this narrowing, and if you switch back and forth, you see that this is the effect here. Okay, so now let's try something else. Let's take this pseudo-bare band structure, and let's do DMFT on that. So this will not be equivalent to the initial GW plus DMFT calculation, because the pseudo-bare band structure was actually a bare spectral function, also with imaginary parts with frequency dependence and so on. So what we do now, we throw away this part. We just construct the density of states corresponding to the non-local GW self-energy only, and then we do DMFT on that. And we compare with what we had for the full calculation, GW plus DMFT, here the black curve, and with the one where you would just do DMFT with dynamic Q on top of LDA. So the green curve is now the new thing, and you see it is kind of intermediate between the full GW plus DMFT and the LDA plus U of omega plus DMFT. In particular, it gives you the same kind of merging of quasi-particle peak and upper Hubbard band. So let's step back. We saw in the ARPIS here the upper Hubbard band at about 2 eV. That is consistent with the static value of U of 3.5 and the position of the lower Hubbard band at 1.5. But it means that, oops, sorry, I'm going in the wrong direction. But it means that the upper Hubbard band, if any, would actually be contained in this peak and is merging with the quasi-particle feature. And this is common to the full calculation and to the one where we do DMFT on top of this pseudo-bare band structure. Okay, final slide. Let's look at things just on the Matsubara axis. This is the slide for theoreticians, really, because here you can look at things without any analytic continuation and so on. So here I have a comparison of the self-energy, and now everything is just the local part. Self-energy of standard LDA plus DMFT, just calculated with a static Q. In red, the LDA plus DMFT with the dynamic Q, so LDA plus U of omega plus DMFT. And in black, the full GW plus DMFT calculation. And in green, this kind of poor man's version, non-local GW plus DMFT. Okay, so what you see is, well, LDA plus DMFT, usual one, lives on a completely different energy scale because it doesn't know about the bare interaction of 15 eV. It just knows about a screened interaction of 3, 4, or 5 eV. This changes entirely the energy scales here. However, it would not be supposed to be correct on these energy scales. So what you should look at is the renormalizations at low energies here. And there you see something interesting, namely that the GW plus DMFT and the simplified GW plus DMFT nicely have a similar renormalization, whereas the LDA plus U of omega plus DMFT overestimates here the correlations. The slope is too steep. On the other hand, if you look at higher energies, at some point the simplified thing deviates strongly from the full calculation, which is normal because in this regime there's no reason that the pseudo-bare density of states should be meaningful. There, the GW approximation has itself imaginary parts, frequency dependence, and so on, and this will make a difference here. However, there you come closer to the LDA plus U plus DMFT with U of omega. Okay, so now let me switch to my second part. How much time do I have, Tanushri?
5 more minutes to be 25.
Okay, good. then I can show you my second example. So now I switch completely to another system, but I keep the same methodology. So the system are atoms on a semiconductor surface. More precisely, I take here silicon with a 1-1-1 surface, and I put atoms. That can be tin, okay, it can be carbon, it can be lead, and I also artificially look at silicon on silicon, even if this, of course, does not correspond to the same state in nature, because it would do some reconstruction. If I look at this series of systems, I realize that the atoms form an isolated band. This is the LDA band structure here, within the gap of silicon. And it is this isolated band here that I will be focusing on. So this is carried by a pz-like orbital here on these atoms, and is nicely separated from the rest of the electronic structure. So now let me calculate the parameters of some low energy effective model that would describe that low energy band. And for the hopping parameters, that's easy. I will here extract the T prime, T double prime, which would parameterize in a tight binding representation this band structure here. And I will also calculate the U within the constrained random phase approximation. I realize, this is not shown here, but I just give you this as additional information, that the frequency dependence of that quantity is not so large, which would correspond to some renormalization of polaronic nature of about 0.9 or something. So we neglect that thing, and we just keep the static part. So then you would say, these are the parameters of a static single band Hubbard model. Okay, but let's continue a little bit before making too much definite statements. If we calculate the intersite interaction, so the interaction that field two electrons that sit on this atom pz orbital on neighboring sites, then we find that this is 0.5 eV. That means, depending on the on-site interaction of the species here, up to 50% of the on-site interaction. So the intersite interaction is by no means negligible. And you can make an additional exercise, and that relates to the question that was asked yesterday, actually. So for this system, this number can be rationalized by saying that you have actually an effective dielectric constant for this silicon system, and that screens the intersite interaction. And if you do just a back of envelope estimate of that size, you get exactly to this number. So that means you essentially have the dielectric screening of the semiconductor, giving you a long-range Coulomb tail. So you have even nth nearest neighbor interaction, which will just be parametrized by this number here and divided by the distance that you have. So we don't have a Hubbard model. We have an extended Hubbard model. A Hubbard model, one single orbital, but with a full long-range Coulomb tail with just a renormalized interaction. Here I've also given you the bare interactions just for comparison. So this is when you just take the matrix element of the Coulomb interaction, the bare one, in this single orbital. So now let's do GW+DMFT. And since we are in this low energy subspace, just extended Hubbard model, things are very simple. Well, not very simple, but at least feasible. So we can do both. Not only this loop for both single particle and two particle quantities, but also the outer one. So we can do also the update of the non-local quantities. And then we find actually that these materials, lead, tin, silicon, carbon, on this semiconductor surface, are situated in this kind of schematic phase diagram, where you have, as a function of the local interaction and the non-local interaction, a Mott insulating phase for huge local interactions, a metal for small interactions, but charge ordering if the intersite interactions are too large. You have these materials situated, well, for carbon deep in the Mott phase, silicon a little bit more down towards the charge order, tin here, and lead actually more or less at the crossing here. And for lead, actually, we converged to two solutions, one metallic and one insulating. So lead is so close to the transition that we find it actually in a kind of coexistence region where we can stabilize both solutions. And one output of the calculation is, of course, the U of omega, where U is now screened not by high energy degrees of freedom, but by the non-local degrees of freedom. Within this low energy single band model, we have now a screened quantity, which is a representative local interaction, which is screened by the full long range Coulomb interaction tail. So this corresponds to the equation that Ferdi discussed, that you have a kind of constrained screening quantity where you take W, the screened interaction, and you unscreen it by the polymerization of the local part only. And this quantity is plotted here, U of omega, here omega, for these different materials. And you see that, for example, look at the curve for tin, that you have a kind of, well, plasmon pole quantity again here, but with much lower energy scale. So here now we are on the scale of 0.8 eV. And that things depend strongly on the material. So for carbon, the frequency dependence is absent, completely flat. We are deep in the Monte insulator, no screening by non-local processes. For tin, as discussed, we have a, well, substantial effect. And interestingly, for lead, we have two U's. We have the one for the insulator, and we have one for the metal, which is logical because screening in these two situations is different. But it also means that if you were taking, for example, the zero frequency value of this U as an effective local U to be put in a low energy model that should, with just a local quantity, reproduce your physics, you should do that with different values for both phases. So if I were trying to downfold again the model with long-range interaction into something with just a local interaction, this local interaction should be different between the two phases. And okay, you can look at the quantity. So this U at zero frequency from GW plus DMFT at the end varies. So from the more or less unscreened value for carbon to something which can be half of the original value, but depends on the phase. So as I said here, corresponds to two Hubbard models. So conclusion of part 2, the local effective Hubbard U that you would use within a representative local problem should actually depend on the phase that you look at. Conclusion of part 1, well, we should more carefully look at unoccupied states. It would be very nice to be able to analyze experimentally the orbital character of this peak, possibly even momentum dependent. So it would be really nice to have something like inverse RPIS or other spectroscopies that could assess the empty states. And with this, I come to the end. Of course, GW plus DMFT still involves approximations, and one should try to go beyond that. For example, spin fluctuations beyond the charge channel, beyond the GW contribution would be interesting to look at, and also to more systematically look at renormalizations of the uncorrelated states. So we have seen P states, D states, uncorrelated states are corrected now, and one should really explore this further. And then, of course, one should go beyond Strontium 108. Okay, references and collaborators. I will not go through all of this, but just mention that for the GW plus DMFT calculations, the main player here was Jan Tomczak, former student. And for the systems of atoms on surfaces, this was mainly work by Philipp Hansmann and Thomas Erral. And finally, a slide maybe for the students here. If you want to know more, if you got interested, I expect to have some postdoc openings, so please come and talk to me. Thank you very much.
Questions and comments? Thomas.
Just one question. The calculation for the, which was carbon, this was charge ordered, the final result, or was that not charge ordered?
No, the carbon is really deep in the mod phase.
Then I meant the other one. Sorry, go back, please. Oh, this was the lead then. Sorry,
The lead.
The
Yes.
lead, the solution was charge-ordered insulator or not?
Okay, so our calculation was such that we can only see that, for example, the thing goes charge-ordered from the divergence in the W. We didn't look in a setup where you would include explicitly the charge order. However, what we can say is that really this compound is very close to the boundary, so we stabilize this in this phase. However, experimentally people are trying to look at this, and experimentally it seems to be very hard to even determine the symmetry if it's a 7 whatever reconstruction, and this may be precisely related to the fact that it's kind of in this region of instability.
But my question rather went into the direction whether the difference between the two U's could be related to charge ordering, but this is not the case.
No, this is not the case.
Both paramagnetic in that sense.
For the charge order phase, you would have a third one.
Yeah, that's what I was wondering.
Yeah. Well, for the charge order phase, you cannot map it on an effective local problem, of course.
Anton.
I have a question. So, basically, it's sort of expected that the effective U is smaller in the metal than in the insulator because there is better screening. So, what you say is that there are some systems, like these atoms, in which this effect is actually very big.
Yeah.
And it leads to big differences in U in the two phases. But what is your opinion of more three-dimensional oxides? I mean, is this difference also big, or is it a small effect?
Yeah,
I mean,
okay. Good question. So let's take, I don't know, V2O3, you're thinking probably of, right? So if we were doing the downfolding just of high energy degrees of freedom, so I'm just backtracking a bit, then of course the thing would be strictly the same because you cut out, not strictly the same, but it would be more or less the same because you cut out precisely the D manifold that you're interested in. However, now we do the second step and look at the non-local screening. There it's a good question. So the full answer is I don't know. I would not be aware of a mechanism which excludes these kind of effects. So I think it's still very much possible. But of course, it can very well be that also this low dimensionality and things play a role. So, yeah. So I think, I think the full answer is this goes in this part. Yeah.
I have a question about, in fact, Faraday touched this point a little bit, but maybe I would ask the question now. Of course, now you could show you and Faraday that by doing this GW plus DMFT, you get a much better description, at least for the systems that you mentioned here. And now going to the 3D systems, when I introduce also the K dependence. So Faraday was saying we see that many effects are in fact compensating. So the question is, which is now the recipe to follow? Because right now you get already, of course for the last materials probably you don't need that much this K dependence, but you need it definitely for most of the systems. So you get already very good answer. Now if I put the K dependence, let's say, I don't know, with DCA or any other method that I can think of, will I spoil the results, or what do you expect? How should one proceed?
Okay. Yeah, okay, very, very good question. So honestly, I believe that in traditional LDA plus DMFT, often this kind of effects of the dynamic U were masked by the fact that we didn't know anyhow the static U. So as Faraday discussed, strontium 108 was calculated with a too large U to get the mass enhancement. The lower Hubbard band was a little bit too far, but okay, at least we had a lower Hubbard band. So I think the question becomes now a quantitative one. If we want to really go towards quantitative comparisons with experiment, then it's not the same doing frequency-dependent U or doing the calculation with a little bit larger static U and in a static way. And this relates back to the question that was asked before about the mass enhancement due to this polaronic effect, because actually we showed, I think I have the reference even. Yes, we showed in this paper here that you can map back a model with frequency-dependent interactions on a static model if you take explicitly the polaronic renormalizations into account for the one particle, particle part. If the energy scale of the plasmon excitations is large enough. That's the caveat. So that means you can go back to a static thing. The question now comes, what should be the initial static band structure? And there I believe this example of strontium vanadate shows that you cannot just assume that you widen a bit, you narrow a bit, and things compensate, because at least in this example, the widening is taking place on the unoccupied part. The narrowing is taking place everywhere. So if you are interested in the quantitative comparison, you will not get away from this. And the second question is also a question of spectral weight, because if you widen and then re-narrow, it's not the same as starting from a narrower band structure at the outset. Because in the narrowing process, you transfer spectral weight to higher energies. But in the widening, you don't. It's just a K renormalization effect. So that means probes that are sensitive to spectral weight should see the difference between just starting from an effective band structure or really do the widening, do the narrowing, and do the calculation. So photo emission, of course, has a hard time to address absolute values of the intensity. And I think this is probably why we have not seen this before. But I think one should try to go more systematically. For example, optics and so on should be able to assess these effects. So the answer is, I think, it's a question of what one wants. If one wants coexistence of Hubbard band and quasi-particle peak, one fits a U, okay. But if one wants to have the quantitative positions and spectral weights, then I think one has to go through this here.
I have one question. For the add atom problem, so you did nothing with the silicon 111 surface.
No.
That is still at the level of LDA.
Absolutely.
Because you are now looking at the whole thing together, but in your add atom problem, you are still restricted to the low energy.
So what we do is really take this low energy subspace, and that was what gave us the possibility to do a full self-consistency everywhere. Because otherwise, with a full silicon in a slab calculation.
Okay, if there are no further questions, let's thank Silke again. And we break for tea. And after that, we have the Chandrasekhar lecture. One announcement that we finally managed to take printouts of the discussion, made a full schedule. So if you are interested, please pick it up.